Hello, and welcome to the TI Precision Labs module discussing the details of RTD measurement circuits. This module covers topics including RTD biasing schemes, ratiometric measurements, RTD circuit configurations, and IDAC compliance voltage. The goal of this module is to better understand the important characteristics of an RTD measurement system. It is possible to bias RTDs using one of two methods. On the left, a constant current source forces a current IDAC through the RTD resistance RRTD, creating a voltage drop VRTD that is measured by an ADC. The equation for VRTD using a constant current source is IDAC multiplied by RRTD. Therefore, VRTD has a linear relationship to RRTD because the IDAC term is constant. This is shown on the bottom left. Comparatively, constant voltage excitation can also be used to bias an RTD, as shown on the right. A constant voltage source, Vref, establishes a resistor divider between the RTD resistance, RRTD, and the divider resistor, RDIV. Similar to the constant current biasing scheme, the ADC measures the RTD voltage, VRTD. The equation for VRTD using a constant voltage source is Vref multiplied by the ratio of RRTD to RRTD plus RDIV. In this case, VRTD has a nonlinear relationship to RRTD because the variable RRTD appears in both the numerator and the denominator of the VRTD equation. This is shown on the bottom right. Due to the inherent nonlinearity in constant voltage biasing, constant current is the most common biasing scheme used for RTDs. Subsequent RTD Precision Labs modules will therefore only consider applications using a constant current source. Now, let's consider the basics of the RTD measurement circuit. Shown on this slide is a basic 4-wire RTD measurement system using a low-side reference resistor, RREF. This circuit includes all the necessary components to measure an RTD, each of which will be discussed in more detail in the subsequent slides. Let's introduce the important features of this circuit. The most critical element of an RTD measurement circuit is the RTD. As discussed in a previous Precision Labs module, RTDs can be configured as 2-wire, 3-wire, or 4-wire. This particular example shows a 4-wire RTD. The RTD is connected to the input terminal block. The terminal block size directly correlates to the number of RTD wires. In this example, a 4-post terminal block is used because we are measuring a 4-wire RTD. Between the terminal block and the ADC is a low-pass filtering circuit. These circuits appear on both the ADC analog inputs and the ADC reference inputs. These filters keep out band noise from aliasing back into the ADC passband. While shown in this diagram, these filters will be removed from the rest of the Precision Labs series on RTDs to keep subsequent diagrams simple. However, an anti-aliasing filter should be included on all measurement channels. A constant current source biases the RTD so the ADC can measure the RTD voltage. The constant current source is often integrated into the ADC. The low-level RTD output voltage is applied to the inputs of a low-noise PGA, gaining up the input voltage and enabling precision measurements. In addition to biasing the RTD, the constant current source also biases the reference resistor, RREF. The ADC uses the voltage across RREF as the differential reference voltage. This configuration is called a ratiometric reference. Finally, a high-resolution ADC compares the amplified RTD voltage to the reference voltage supplied by RREF, and then generates the ADC output code. Let's discuss these features in more detail, beginning with an analysis of how the current source biases the RTD. This figure is the same 4-wire RTD measurement circuit shown on the previous slide, though the input filtering circuitry has been removed for simplicity. Let's apply constant current source, IDAC1, to the ADC and see how the circuit behaves. The red current from IDAC1 flows out of the IDAC pin, passes through the top lead resistance, the RTD, the bottom lead resistance, and then continues on through RREF to ground. As a result, a voltage is established across RRTD and RREF that can be measured by the ADC. The voltage across RRTD, or VRTD, is the product of RRTD and IDAC1. Shown in blue, this voltage is applied to the ADC inputs, amplified by the PGA, and then measured by the ADC. Similarly, the voltage across RREF, or VREF, is the product of RREF and IDAC1. Shown in orange, this voltage is applied to the ADC's differential reference voltage inputs and used as the ADC reference voltage. The resulting ADC code is proportional to the ratio of VRTD to VREF. This ratio is equivalent to the ratio of RRTD multiplied by IDAC and RREF multiplied by IDAC. The IDAC1 term in both the numerator and the denominator cancels out, and the resulting ADC code is just the ratio of RRTD to RREF. Importantly, this relationship reveals that the ADC code is independent of the absolute value of IDAC1. In other words, any variation in IDAC1 will be seen equally in the input voltage and reference voltage, and therefore cancels out. This is called a ratiometric reference configuration. All subsequent diagrams and analysis in this Precision Lab series on RTDs use a ratiometric reference. An absolute reference voltage can be used but is not recommended for RTD measurement systems. One additional consideration for a ratiometric reference is that the RREF term should be a constant value. If RREF varies, the ADC output code will also vary, causing measurement inaccuracy. It is therefore imperative to choose a high-accuracy, low-drift resistor for RREF. A 0.1% accurate component with a 5 ppm per degree Celsius drift specification is recommended. Let's move on and discuss another important characteristic of an RTD measurement system, the total circuit resistance. The total circuit resistance, or R total, is defined as the total resistance between the IDAC output and ground. Shown on the left is the same 4-wire RTD system from the previous slide. As in the previous diagrams, there are two lead resistances, the RTD resistance and the reference resistor in the path between the IDAC output and ground. This diagram also includes additional resistance in the IDAC path that might be required for certain applications. The table on the right explains each resistance type in more detail. For example, the protection resistor, RProtect, might be required to limit the current into the IDAC pin in the case of an overvoltage event. The miscellaneous resistors, RmiscellaneousH and RmiscellaneousL, might be the on resistance of a multiplexer used in a multi-RTD measurement system. The bias resistor, RBias, can be required to level shift the RTD voltage into the input range of an amplifier circuit. Note that not all of these resistances are required in every RTD measurement system, but if they are included, they must be accounted for in the total circuit resistance. The equation shown here calculates R total for this system. At this point, it is natural to wonder, why is R total an important system parameter? The total circuit resistance, R total, is an important system parameter because it directly impacts the IDAC compliance voltage. On the left are some key points about the IDAC compliance voltage. The IDAC compliance voltage defines the minimum difference between AVDD and the voltage at the IDAC output pin that enables the IDAC to maintain constant current. The voltage at the IDAC output pin is the product of R total and IDAC. The IDAC compliance voltage is typically specified to 0.1% accuracy. Finally, the selected output current can change the maximum compliance voltage. For example, the ADS124SO8, a 24-bit low-power Delta Sigma ADC, has two well-matched current sources integrated into the device. This ADC acts as a complete RTD measurement system, including the biasing circuitry. The ADS124SO8 IDAC specifications are shown in the table on the top right. Note that these IDACs require a minimum of 400 mV of headroom between the IDAC output pin voltage and AVDD to maintain constant current. However, at output currents greater than or equal to 1 mA, the compliance voltage increases to 600 mV. In both cases, respecting the compliance voltage guarantees a maximum 0.1% deviation in the IDAC output current. what happens when the compliance voltage is violated? This image, taken directly from the ADS124S08 datasheet, plots the IDAC error in percent as a function of the IDAC output voltage when AVDD equals 3.3 volts. Note that as the IDAC output voltage increases beyond the maximum compliance voltage, the IDAC error increases rapidly and significantly. Instead of 0.1% error, the IDAC output for all current settings quickly drops to an error of 5% or more when the compliance voltage is violated. As the IDAC output voltage approaches AVDD, the constant current source begins to act like a constant voltage source, thereby changing the behavior of the entire RTD circuit. It is recommended to design a system that always respects the IDAC compliance voltage, which requires a balance between the AVDD voltage, the IDAC output current, and the total circuit resistance. Now, let's understand how to convert the measured ADC output code to a temperature. Shown here is the generic ADC code equation. The specific ADC code that correlates to the input voltage is equal to the total number of codes multiplied by any circuit gain, which is multiplied by the ratio of the input voltage to the reference voltage. Note that the reference voltage can have a scaling factor denoted by a capital A in the equation shown here. This scaling factor is defined by the ADC full scale range equation found in the datasheet and can be different from device to device. As an example, A equals 4 if the ADC full scale range is equal to plus or minus 2 multiplied by Vref divided by gain. For an RTD system, the RTD and reference voltage are given by the equation shown here, which was derived earlier in this presentation. The IDAC term cancels out because it is in both the numerator and denominator of this equation, resulting in a modified version of the ADC code equation. In this new equation, the RTD and reference voltages are replaced with the RTD and reference resistances, respectively. This allows us to solve the ADC code equation for RRTD. Highlighted in yellow is the new ADC code equation that solves for RRTD. A critical takeaway from this equation is that RRTD directly depends on the values of Rref and the gain. As mentioned previously, ensure that Rref is a high accuracy low drift resistor while also minimizing the system gain error. Taking these steps will help maintain overall system accuracy, which is discussed in more detail in a subsequent Precision Labs module. Now that we have an equation for RRTD, we can use equations or lookup tables to correlate the RTD temperature to the measured resistance. These options are shown on the right. While the benefits and challenges of each resistance to temperature conversion method were discussed in a previous Precision Labs module, one additional consideration that we need to account for is the resolution of each method. A polynomial equation will be more difficult to implement in a microcontroller, but it is theoretically possible to determine the temperature of any measured resistance. The resolution of a polynomial is therefore only limited by the computational power of the controller. Comparatively, a lookup table has a fixed resolution, which in this case is 1 degree Celsius. If the ADC resolution is greater than the resolution of the lookup table, the measured resistance calculated from the ADC output code can be between two values in the table. How do we resolve this issue? The most common way to identify intermediate temperatures from a lookup table is to use linear interpolation. This method is used because the process is computationally simple compared to using polynomial equations. As its name implies, linear interpolation assumes that the response of the RTD resistance versus temperature curve is linear between any 2 points. If this is not the case, calculation errors can occur. This is discussed in more detail in a subsequent Precision Labs module. As an example, assume that the calculated ADC code yields a measured resistance of 131.5 ohms, which is highlighted in green. Let's use linear interpolation to calculate the corresponding measured temperature. To begin the process, the table on the left highlights the next smallest and next largest resistances compared to R measured. The resistance value less than R measured is called R1, and the resistance value greater than R measured is R2. These values are shown in the top right along with their corresponding temperatures. Next, we will need the general equation for a line, which is the first formula shown on the right. Then, we calculate the slope using the second equation. Entering R1, R2, T1, and T2 into the equation yields a slope of 2.632 degrees Celsius per ohm. With the slope calculated, determine the y-intercept by applying either resistance-temperature pair to the equation for a line. R1 and T1 are used in this example, which results in a y-intercept of negative 264.474 degrees Celsius. Finally, we can use the derived equation for a line to calculate that T measured is 81.585 degrees Celsius. Now that we have discussed several important RTD measurement system parameters, the next few slides introduce the various ways RTD circuits can be configured. All of the RTD measurement circuits shown in this presentation so far have used a 4-wire RTD with a low side reference resistor, similar to the image on the left. A low side reference resistor positions RREF between the bottom of the RTD and ground as shown. However, the image on the right shows an RTD measurement system using a high side reference resistor. In this case, RREF is between the IDAC output and the RTD. An optional bias resistor, RBias, is shown between the bottom of the RTD and ground. This resistor can be required when RTD output voltage is applied to a PGA with common mode input voltage limitations. RBias level shifts the RTD output voltage into the linear operating range of the PGA. One of the main benefits of a high side reference resistor is that it provides some inherent overvoltage protection for the IDAC pin. When an overvoltage event occurs on the top terminal of the 4-wire RTD, RREF limits the current into the IDAC pin to avoid device damage. Refer to the ADC datasheet to identify the absolute maximum pin current and then design the system accordingly. Also note that ANP, ANN, REFP, and REFN are inherently protected by the respective filter resistors, which are not shown on these diagrams. One of the disadvantages of a high side reference resistor is the need for RBias. However, this component does not need to be high accuracy and low drift like RREF, so there is little additional cost. In reality, there is little advantage to choosing a high side versus a low side reference resistor to measure a single 4-wire RTD. This choice matters considerably more when the system is measuring a single 3-wire RTD using 2 IDACs, or when designing a multi-RTD measurement system. Both of these topics are discussed in more detail in subsequent Precision Labs modules. Next, let's discuss the different RTD wiring configurations. As noted in a previous Precision Labs module, there are 3 common RTD configurations. The first RTD wiring configuration is the 2-wire RTD shown on the left. This is the simplest and most cost-effective configuration. However, one important characteristic of an RTD is that each RTD wire has some lead resistance, R lead. When the RTD is biased, current flows through the sensor along the path in red. In the case of a 2-wire RTD, both lead resistances are part of the measured input and cannot be automatically removed. While this lead resistance is typically negligible when the RTD wire length is short, some applications can require very long leads. In such an application, very long RTD sensors can have significant lead wire resistance compared to the RTD resistance. As a result, 2-wire RTDs are typically used for lower accuracy systems. The next type of RTD wiring configuration is a 3-wire RTD, shown in the middle of this slide. Similar to a 2-wire RTD, each wire has some lead resistance, R lead. Unlike a 2-wired RTD, the measured input only includes one R lead, which can automatically be removed from the measurement using 2 different methods. The first method uses a single current source and is shown on this slide. The second method uses 2 current sources. Both of these methods are discussed in more detail on the next slide. The final RTD wiring option is a 4-wire RTD, shown on the right. Like 2 and 3-wire RTDs, each wire in a 4-wire RTD has some lead resistance. However, the bias current only passes through our lead in the top and bottom legs, which enables direct measurement of the RTD resistance without any influence from our lead. In other words, a 4-wire RTD provides inherent lead wire resistance cancellation, though This feature causes 4-wire RTDs to be the most expensive type. As stated in the top right, all of the RTDs shown here use a low side reference resistor to generate the ratiometric reference voltage. However, each configuration can also be used with a high side reference resistor. Finally, as mentioned on the previous slide, 3-wire RTD systems can use 1 IDAC or 2 IDACs for automatic lead cancellation. Each of these methods has advantages and disadvantages. On the left is a 3-wire RTD system that uses a single IDAC to bias the RTD. To implement lead resistance cancellation, 2 measurements are required. The first measurement occurs between A in P and A in N, which measures the combined voltage across R RTD and R lead 1. The second voltage measurement occurs between A in N and A in COM, which measures the voltage across R lead 3. Assuming R lead 1 equals R lead 3, the final result is the difference between the first and second measurements, which is just R RTD. The benefit of this method is that it avoids any mismatch error between the 2 current sources. The challenge with this method is that it requires 2 measurements, which doubles the measurement time compared to the 2 IDAC method. Comparatively, a 3-wire RTD system that uses 2 IDACs for automatic lead cancellation is shown on the right. Note that in this case, only IDAC 1 is used to bias the RTD. The second current source, IDAC 2, creates a voltage across R lead 2 that has the same magnitude as R lead 1, but the opposite sign. Therefore, the difference between A in P and A in N is the voltage across R lead 1 plus R RTD minus R lead 2. Assuming R lead 1 equals R lead 2, the result is just the voltage across R RTD. However, this result requires an additional assumption that the current output from IDAC 1 and IDAC 2 are identical. Any mismatch in the IDAC currents results in an error. As stated in the top right, both RTD measurement systems shown here use a low side reference resistor to generate the ratiometric reference voltage. However, each configuration can also be used with a high side reference resistor. Note that the analysis for a 3-wire RTD using 2 IDACs changes between a high side or low side reference resistor. When using 1 IDAC, the analysis is the same. 3-wire RTD configurations are discussed in detail in a subsequent RTD Precision Labs module. This presentation introduces the most important RTD measurement system parameters. Some of the possible RTD configurations were also introduced, though not all combinations and not in detail. For more comprehensive information about how each circuit behaves, review the application note, A Basic Guide to RTD Measurements. To navigate to this application note, click on the link at the bottom of this slide, or search for the title A Basic Guide to RTD Measurements on TI.com. That concludes this video. Thank you for watching. Please try the quiz to check your understanding of this video's content. Question 1. What does the compliance range specification of an IDAC indicate? The correct answer is A. The IDAC compliance voltage indicates the voltage range at the IDAC output pin over which the IDAC can maintain constant current within some defined deviation. Question 2. True or false? The reference resistor, RF, does not need to have good accuracy, as the ratiometric properties of the reference eliminates initial tolerance errors. The correct answer is B. False. Choose a high accuracy, low drift reference resistor for high performance RTD systems. Question 3. One advantage of a high side reference resistor is that it can offer some protection against electrical overstress. What is a disadvantage to this method? The correct answer is B. An extra bias resistor can be required to keep the input in the proper common mode range. Question 4. True or false? When using a ratiometric reference, errors in the biasing current cancel out because the RTD output and reference scale proportionally. The correct answer is A. True. That's all for today's video. Thanks for watching.